Let's turn to the concept of complex exponents. We have that it's possible to prove that the set in C, when C is n, an integer n, then this number is equal to the exponential function of n times the logarithm of set. This is rather easy to show, and it's also possible to show that if we take set to the power of 1 over n, which means the nth root of set, it turns out to be equal to the exponential function of 1 over n multiplied with the logarithm of set. So it's natural to generalize this for a value of set which is not an integer, but which is an arbitrary complex number in the complex plane. So then we have set to the power of c is defined as the exponential function of c multiplied with the logarithm of set. And this can be multiple valued. So let's give an example of this. Find I to the power of minus 2i. What's that? Well, we know from this formula the definition of what this means, that we should have I in minus 2i is equal to, we just replace in this definition c with minus 2i, and set is in this case I. So we just have that this number is defined in the following way, and then we just have to find the logarithm of I. So the logarithm of I is just like this. It's the logarithm of the absolute value of I, which is 0, plus the principal argument of I, which is pi over 2, plus 2 pi k, and multiplied with I. So then we insert this into our formula and obtain this. And we can now multiply I with I, which is minus 1, and obtain this expression. So in our case we obtain that I to the power of minus 2i is equal to multiple values, namely these values for k integer valued. It follows by the definition that this 1 over c to the power set to the power of set c is equal to set to the power of minus c. Let's take an example of this. What does this mean? Using this formula, we have that 1 over I to the power of 2i is equal to I to the power of minus 2i, which is equal to, we have computed it above, equal to this. We can also consider branches of these exponents. The branch, when we have which we have illustrated here, which goes from from minus pi plus alpha to pi plus alpha, using this branch for the principle, for the argument here, which is a unique function. Then we have discussed this before, we get this logarithm which is uniquely defined. And as we have discussed before, the derivative in this set, except for this line here, is equal to 1 over set. So if we now use logarithm in this branch, then we obtain the following by differentiating set to the power of c with respect to set. We use just the definition of what we mean with set to the power of c as defined above, and we know the derivative of the exponential function, so we therefore can use the chain rule to find the derivative of this function. So the derivative of the exponential function is just the exponential function itself here, and we multiplied with the kernel of this, which is the kernel is this, and the derivative of this is of course this c, which is a constant, multiplied with the derivative of the logarithm of set, which is 1 over set. So therefore we obtain this expression for the derivative of set with to the power of c.